In FSCRIPT, there are over 30 different commands. But don't worry, they're grouped into just a few categories. Some commands help you control script flow. Some help you display information. Some are for setting up CAN networks and talking to ECUs. And then you have advanced commands for logging, file handling, and ECU reprogramming. We'll go through each group step by step, and I'll show you real examples so you can build your own scripts easily. In this section, let's go through some basic control commands and display commands that you'll use all the time in FSCRIPT. These are the building blocks, stuff like delays, showing text, waiting for a button press, and simple logic checks. Let's start with delay. If you want the script to wait for some time, you use the delay command. The delay must be specified in milliseconds. It's super simple. Check out the example, delay 1000. That'll pause the script for 1000 milliseconds, or basically 1 second. Next is the exit command. When you want to stop your script, like if something fails or you're done, just use exit. It'll exit and go back to the main menu on the MyCANIC device. Next is the but LED command. You can control the red and green LEDs on the MyCANIC using this command. Example, LED green on. This will turn on the green LED. LED red off. This will turn off the red LED. You can even toggle an LED to blink it every time your script loops. Now, let's move to the get key and wait key commands. So first, get key command. Get key is used when you want to check if a key was pressed, but you don't want to stop the script while checking. Meaning, the script will call get key, quickly check if something was pressed, and immediately move on, whether or not a key was pressed. It doesn't wait. It's like a, did someone press anything? No? Okay, keep going, kind of thing. After you call get key, the key that was pressed, if any, gets saved into a special variable called key. You can then use that key in your logic. Check out the example. So here, if the escape key was pressed while the script was running, it'll catch it and exit. Otherwise, it'll just move on normally. Now, wait key. Wait key is different. Wait key will actually pause the script and sit there waiting until a key is pressed. The script won't move forward until the user presses a key. You can make it wait for specific keys like wait key enter, wait key escape, wait key any. Check out the examples, wait key enter. Here, the script will completely stop until the user presses the enter key. Nothing else will be accepted. If the user presses some other key, it won't continue. You can also do wait key any. That means I don't care which button you press. Just press something so we can move forward. Real world tip to use get key inside loops when you want the script to keep doing something, but still be watching for a cancel button. Use wait key when you need the user to confirm or decide to move forward. One important thing, after using the get key or wait key command, the press key is always stored in the key variable. Next, let's dive into how to show information on the screen using LCD and HLCD commands. So first, LCD. The LCD command lets you display any text, number, or even live data on the MyCANIC screen. The basic format looks like this. LCD followed by row and column number, followed by what to display, followed by optional fields, multiplier, and offset. Now, let me break that down. Row is from 1 to 15. That's top to bottom. Column is from 1 to 26. That's left to right. What to display can be just simple text or real data from the vehicle, like VN, battery voltage, diagnostic responses, anything you want. For example, just displaying some text. LCD row 1, column 1, hello world in double quotes. This will show hello world starting at the top left corner of the screen, row 1, column 1. Now, suppose you want to clear part of the screen. You can display an empty string at any row column like this. LCD row 2, column 1, then just blank quotes. This will clear everything from that spot to the end of the screen. In this case, it will clear the screen from row 2, column 1, to the end of the screen. Now there's also HLCD. HLCD works exactly the same as LCD, but the text will show up highlighted, meaning it'll be bold or visually emphasized on the MyCANIC display. It's great when you want to catch the user's attention for something important. For example, HLCD row for column 1 error. Error will be displayed as highlighted text. Besides just showing normal text, you can also display data from the vehicle. Like, if you read a VIN or battery voltage, you can put it on the screen dynamically. For example, after reading data, LCD row 2 column 4, data 01. Here, data 01 means display 1 byte starting at index 0 of the last response buffer. You could also show hex, text, and float values, depending on what you want to display. Another super common example is displaying battery voltage. LCD row 3, column 5, VBAT. That will show live battery voltage in millivolts. Let's talk about the optional fields, multiplier, and offset. If you want to adjust the display, like scaling a value or adding an offset, you can add a multiplier and offset at the end of the LCD command. For example, LCD row 4, column 1, data 72. Here the multiplier is 0.001 and the offset is 0.0. This means take a 2-byte value starting at index 7, multiply it by 0.001, for example, converting millivolts to volts, and add an offset of 0.0. This is super useful when you want to clean up engineering values without rewriting scripts. Real-world tip. See, when showing important information like VIN, module ID, or errors, use HLCD so it pops out visually. If you're updating a value on the screen inside a loop, like a counter or voltage, remember to clear that part of the screen first using LCD row, column, blank quotes. Otherwise, old numbers might overlap. All right, so that's a quick look at the basic commands. Delay, exit, get key, wait key, get time, LCD, HLCD, and LED. In the next part, we'll put together a mini project and use all the commands we learned so far. Now let's build a mini project. We're going to display some instructions, wait for the user to press a button, and depending on what button they press, we'll toggle the green LED or the red LED. If the user wants to exit, they can also press the escape key. All right, here's how the script works. Step by step. HLCD row 1, column 1, mini project 1. This highlights mini project 1 at the top of the screen. Next, using these 2 lines, the user knows to press enter to continue. We wait for the enter key using the wait key command. Once the enter key is pressed, we clear the screen and show the options the user has using the LCD command. Now the user knows all the choices they have. Then we use the wait key command to wait for any key press. After that, we check what key is pressed using if-else and the key variable. If pressed escape, we show do nothing, adding a delay of 2 seconds, and then exit. If pressed the right arrow key, we clear the screen, show toggle green LED on the screen, turn the green LED on, delay for 2 seconds, turn it off, and then exit. If pressed the left arrow key, we do the same thing, but with the red LED instead. Real-world tip. Always clear the screen before updating with the new instructions, otherwise old text will overlap. Give users a second or two to see what action was taken before exiting. If you need more responsiveness, you can adjust the delay to be shorter, but 2000 milliseconds, 2 seconds, is a good user-friendly value. That's it. In just a few lines of FSCRIPT, we built a simple but fully interactive tool where the user chooses what to do by pressing buttons. In the next part, we'll move into setting up a CAN network and sending your first diagnostic messages with FSCRIPT. Now that we've covered the basics, let's get into something really important: setting up your CAN network and initializing diagnostics. Whenever you're working with FSCRIPT, whether you want to read DTCs, request DIDs, or flash a module, you need to first set up the communication. There are 3 main commands we use here: net, diag, and periodic. Let's go through them one by one. First up is the net command. This command is used to tell MyCANIC which CAN network you want to talk on, what type of IDs you're using, and what speed the network is running at. Here's the format: nnet followed by network type, followed by CAN ID bits, followed by baud rate. Network type can be CAN_HS for normal high-speed CAN, pins 6 and 14, CAN underscore FD underscore HS for CAN FD high speed, CAN underscore MS for medium speed CAN, pins 3 and 11, CAN underscore FD underscore MS for medium speed CAN FD. CAN ID bits is either 11 standard or 29 extended. Baud rate is typically 500K for high speed, 125K for medium speed, but it depends on the vehicle or module. Check out the examples. First one is setting up high-speed CAN, 11-bit IDs at 500 kilobits per second. Next is to set up medium-speed CAN, 29-bit CAN ID at 125 kilobits per second. The last one is to set up high-speed CAN FD, 11-bit CAN ID at 500 kilobits per second baud rate. Once the network is ready, we need to initialize the diagnostic filter of a specific ECU. That's where Diag comes in. Diag sets up the filter to match the ECU you want to talk to, like the PCM, BCM, TCM, anything. Here's the format. Diag followed by protocol ID, followed by request and response ID. The protocol type is usually ISO 14229 for UDS Diagnostics, or KWP 2000 for older modules. Request ID is the CAN ID you send messages to. Response ID is the CAN ID the ECU responds back on. Check out the example. Set up diagnostics filter for PCM module Diag, followed by ISO 14229, followed by request ID hex 7E0 and response ID hex 7E8. In the next example, we are setting a diagnostic filter for body module using the protocol type KWP 2000. Important note, the Diag command must always come after the net command. Net sets up the CAN network. Diag sets up which ECU to talk to on that network. Also, if another Diag command is run later in the same script, it will override the previous one. So only the most recent Diag command will be active. The older one gets replaced. All right, next is the periodic command. This is used when you want to send a message on repeat at regular time intervals, like every second, every 5 seconds, etc. Format for using this command. Type can be SID or MSG. Timing is how often to send, in milliseconds. Data is what you want to send. Example, send a tester, present message every 5 seconds. Next is to send a custom CAN message every second with a CAN ID hex 123 and 8 data bytes. Real tip, always stop the periodic message once you're done by doing this. Otherwise, the tool keeps sending it forever. Now, why is this simple command very important? One of the most important use cases for this is sending a tester present message. So, what is a tester present message and why does it matter? Well, whenever you start a diagnostics session or reprogramming, the ECU expects to see some activity. If it doesn't, it assumes you're done and automatically exits the session. To avoid that, we need to keep the session alive, and that's exactly what the tester present 0x3e message does. You send this message every few seconds to let the ECU know, hey, I'm still here, keep the session open. If you skip this, the session might time out, which can interrupt logging, break diagnostics, or even kill a reprogramming in the middle, which no one wants. Now that we've set up our CAN network and diagnostics session, let's talk about the 3 commands you'll use constantly to actually communicate with the ECU. These are your go-to commands when you want to send diagnostic messages or CAN messages and work with the ECU's response. First is the write command. The write command is used to send a message. You can use it to send a UDS diagnostic request to an ECU, a raw CAN message, or a USB message. Syntax is write, followed by type, followed by data. Type can be, say, ID for diagnostic service messages. For example, service ID 22, service ID 10, service ID 31. MSG for raw CAN messages with CAN ID and data. USB sends message over USB. Example 1, send a diagnostic request. This sends a service 22 for DID F188, used to read the software part number. Example 2, send a CAN message. This sends 8 bytes to CAN ID 123. Real-world tip. The write command just sends the message. If you want to get the response, you must call read immediately after, or use request, which handles both. Next is the read command. The read command is used to capture the last response received, whether it's from a diagnostic command or CAN broadcast. The data is stored in internal FSCRIPT buffers like data, text, float, etc., which you can use for comparisons, logging, or display. Syntax. Read followed by type. Type can be SID reads last SID response, MSG reads last CAN message with a specific CAN ID, USB reads last USB input. Example 1, read response to a diagnostic write. Response to the diagnostic write, F188 is stored in buffers like data, text, hex. Example 2, read last CAN message with ID, 0x123. This will store the data from the last message with that ID into the internal buffers. Real-world tips. Always read immediately after write if you expect a response. You can combine it with LCD or LOG to store what you received. Now, if you want to do both write and read in one step, FSCRIPT gives you a shortcut, the request command. Request is the shortcut command that does both. It sends a diagnostic request and waits for the response. Internally, it's the same as doing write SID and then read SID, but with 2 built-in retry logic. The format is request followed by data bytes. Just give it the service ID and parameters. That's it. For example, request service 22, F188. This will send a request to read did F188, wait for the response, and store the result in the same buffers. Data, text, hex, etc. FSCRIPT also has fRequest, or fast request. There's also fRequest, which stands for fast request. It works the same way, but waits only 500 milliseconds and doesn't retry if the ECU doesn't respond. The difference? Request command tries up to 2 retries if no response. fRequest command tries once and moves on. So if you're doing something time-sensitive or non-critical, fRequest saves time. All right, now let's talk about something super useful, the log E command. This is how we create log files in FSCRIPT to save things like VINs, part numbers, voltages, or anything you want from the ECU or CAN messages. It saves data in a nice clean CSV format, so you can open it in Excel later and review all the entries. The log command has 3 main parts you need to understand. File creates the log file. New starts a new row. Add adds data to that row. Let's understand one by one. First is log file, start logging. First, we need to tell FSCRIPT what file to create. We do that like this. Log file vin.log in double quotes. This creates a log file called vin.log on the SD card. If the file already exists, it will keep appending new data, so you won't lose anything. Important? You should only have 1 log file command per script. If you accidentally add more, only the first one will actually work. The rest are ignored. Next is log new, start a new row. Once the file is ready, use log new to start a new row of data. Example, log new p 708 update v 1.00 in double quotes. This means we're starting a new row with the first field entry, the name and version number of the script. This is kind of like saying, all right, new row, let's start logging now. Next is log add more columns. Then you can use log add to add more values to that same row. For examples, log add text 716, log add vbat, log add data 72 with multiplier and offset 0.01 and 1.0 respectively. You can add text, VINs, voltages, DIDs, even values with multipliers and offsets. These show up as separate columns in the CSV file. Super helpful when you're logging multiple things in one shot. Pro tips. Make sure you've already done a read or request before logging. Otherwise, there's no data in the buffer. You can combine this with get time and time if you want timestamps too. Want to mark logs by vehicle? You can use VIN or part number as the first field. Makes sorting later super easy. Where to find the file. The low-G file gets saved directly to the SD card inside the MyCANIC device. You can open it on a PC using Notepad, Excel, or any CSV viewer. It's just plain text, super easy to parse. To summarize, the flow is always log file to create, then log new to start on a new row, then log add to add in the same row. In the next project, we'll actually read a VIN and module ID, display it, and log it all together using what we've learned. All right, let's move on to mini project 2. In this project, we're going to check the battery voltage, read and display the VIN, read the PCM module's software part number, log both to a log file on the SD card. Let's go through it line by line. First, we display a title using highlighted text, just to label the screen using the HLCD command. Then we turn off both LEDs to start clean. Now we start the log file using the log file command. This creates a new log file in the SD card. If already created, it will append to the existing log file. Using the log new command, the first entry is the script name plus version, always good for traceability. Next, we check the vehicle battery voltage before doing anything. We are clearing the screen to display checking VBAT on the screen. If the voltage is below 11 volts, we turn on the red LED, show a warning on the screen, display actual voltage, wait for any key, then exit. It's a safety check. No point in proceeding if the ECU might shut off mid-session. The next step is to set up the CAN network and initialize the diagnostic filter for the PCM module. If VBAT is fine, we go ahead and set up CAN communication. This sets up a high-speed CAN network with 11-bit CAN ID and a 500K baud rate. Using the diag command, we initialize the filter to talk to the PCM module, whose request ID is hex 7E0, and response ID is hex 7E8. Next is to wake up the secure gateway. This is an optional step, but it is a good practice to do this. Here, we are pinging the module to make sure that the module is awake. We are handling that by writing did D100 using service ID 22. Then wait a bit by adding a delay of 200 milliseconds. Even if the vehicle doesn't need this, it doesn't hurt to include. It's just a precaution. Now we read the VN using the standard OBD mode 9 request. After that, we check if the response looks valid. Hex 49 is the expected ECID response for a mode 9 VIN read. If it's wrong, show an error message. Let the user press any key. Exit the script. If the VIN was read correctly, we log it using the log add command and display it on screen. Next, we requested F188 for the PCM software part number using service 22. Then check if it responded with hex 62, which is the positive response for service 22. If it didn't respond correctly, turn on the red LED, log the error. Display an error on screen. Let the user exit manually. If it did respond properly, log that we're storing the PCM F188 value and log the value from the text buffer, then show it on the screen. At the end, we are asking user to press Enter key and waiting for key press using the wait key command. Let the user exit cleanly when they're ready. This is a great real-world project. It checks power, logs key data, handles failure cleanly, and gives user feedback at every step. These patterns, check, log, confirm, are going to come up in almost every serious script you write. All right, so once the script runs and everything goes well, this is how the log file looks on the SD card. I've run the script 3 times on different vehicles, and you can see each run adds a new row in the log. Let's break down what we're seeing here. The first column, Mini Project 2V 1.00. That's from the log new line in the script. We're using that to label the script version. Super useful when you're running different versions in the field. The second column, that's the VIN, logged using text buffer after reading it from the OBD mode 9 request. Third column, PCM F188, just a label so we know this is the module part number. Last column. That's the actual software part number, also pulled from DID F188. As you can see, every run creates a new row. That's because we use a log new once per script run, and then log add to build out the rest of the fields. All right, let's talk about DAT commands in FSCRIPT. These are used to save ECU data, like DIDs or VINs, into a .dat file on the SD card. And then later, you can use that file to recall, rewrite, or even recover a module that's missing data after reflash. These commands are critical for safe reprogramming, especially when you're flashing modules that wipe part numbers or config data. Now, what is a .dat file? A .dat file is a special data file that FSCRIPT creates automatically when you use these commands. It's named using either the VIN or a DID value, depending on what you choose. On MyCANIC IoT, the file name can include the full VIN plus CAN ID or DID value with a .dat extension. First step is always D8 to _init. It tells FSCRIPT, hey, we're about to work with data, set up the buffers. You can initialize using either VIN or a specific DID. Example, dat init VIN. This means we're going to store data in the file based on the vehicle VIN. Or dat init did hex F18C. That means we're going to store data in the file based on the serial number of the ECU. Now, let's move on to the dat create command. After initializing, we use dat create to start building the file. This command actually creates the data file either based on VIN or a diagnostic DID. Example, at create VIN. This creates the actual DAT file using the full VIN plus CAN ID of the ECU. Check out the file name on the right. There's full VIN _ CAN ID of the ECU. Next example, DAT create did hex F188. This creates the data file using the DID value. Check out the file name on the right. It's the software part number of the ECU. Moving on, to actually write the data in the file, you have to use did save command. I will cover did commands in the next section. For now, let's focus on dat commands. Next is the dat check command. Once you're done saving all the dids, use dat check to mark the file as complete. Example, dat check VIN, this seals the file. It tells FSCRIPT this file is valid and finished. Moving on to the dat delete command. As the name suggests, this command allows you to delete the dat file. If you created the data file based on VIN, use dat delete VIN. If you created using a diagnostic DID, then use dat delete DID, followed by the specific DID value. All right, let me show you a complete example of how we use dat commands in a real script. This is the full flow I use when I want to save DID data before doing any flashing, or just to back up vehicle configuration. And we're going to walk through it line by line. First, I use dat init VIN. This tells FSCRIPT, we're about to work with the DAT file and we want it to be based on the VIN. It sets up all the internal stuff and gets the file buffers ready. Then we check if a data file already exists and if it's valid. For this, we use dat status variable. I forgot to mention this earlier, but dat status is a special internal variable in FSCRIPT. It tells you the current state of the DAT file. If dat status equals sign 2, that means the file exists and it was properly completed with dat check command. So we just reuse it. No need to save everything again. If the file exists but wasn't completed properly, FSCRIPT will return one. In that case, we don't trust the file, so we delete it and start over. We delete using the dat delete command. Now that we've handled all that, we go ahead and create a fresh file using dat create command. Now we save whatever configuration data we want to back up. Finally, and this part is super important, we finish the file with dat check command. This marks the file as complete and valid. If you skip this, FSCRIPT will leave it in a half-written state and dat status will stay at 1 the next time you check. It's one of those flows that seems a bit long at first, but once you get used to it, it becomes second nature, especially when working with critical ECUs where configuration data matters. Now let's talk about did commands in FSCRIPT. These are used to do 5 operations: save, recall, compare, modify, and write data identifiers, or DIDs, on the ECU. Here's the syntax for did commands, but all commands requires all the fields. If you've worked with UDS before, you know DIDs are basically memory values inside the ECU, things like VN, part number, config flags, and more. Let's go through each one in detail. Did save. This one's straightforward. It reads a did from the ECU and stores it into the currently open .dat file. Example, did save hex F188. This will grab the current value of did F188 and save it into the DAT file you created with dat create. Did recall. This command pulls a previously saved did value back into the FSCRIPT buffer, so you can use it in logic, display it, or log it. Example, did recall hex F188. Now, the value from .dat gets loaded into data and text, which you can use in logic comparisons, just like if you did a did request. Now here's where did recall becomes a total game changer, especially during reprogramming. When you're flashing an ECU and you're already inside a programming session, you can't just send a normal did request in the middle of the process. The ECU won't respond to any did requests. It's busy downloading the file. That's where did recall comes in. Instead of trying to request the part number live, FSCRIPT just pulls the previously saved value directly from the .dat file. No request, no timeout, nothing to wait on. This is super useful when you're working with DIDs that have multiple part number variations, and each one might require a different flashing sequence. You can build logic around the recalled value, even inside a flash script, which wouldn't be possible if you were relying on a live did request. So yeah, did recall saves you from getting stuck or bricking ECUs, especially when things go wrong mid-flash. Did compare. This is your built-in validation check. It compares the current live value of a did to what you previously saved. Example, did compare hex F188. If the current value doesn't match what's in the .dat file, FSCRIPT will immediately terminate the script. So it's great if you want to ensure a vehicle hasn't changed before proceeding with a flash or config. Did modify. This command lets you edit a few bytes inside a did without rewriting the whole thing manually. You can use basic math or bitwise operations like plus and vertical bar or equal sign. Example, this reads did DE01, goes to byte offset 2, modifies 1 byte, uses bitwise and with 0 XFE. This clears the least significant bit. It's useful for toggling flags or applying tweaks without having to hand edit the whole did. Did write. This command takes a did value that was previously saved in a.at file and writes it back into the ECU. Example, did write hex F188. This uses service 0 x2e to write the value. Great for recovery if a flash wipes out your part number. It's especially powerful because it can run even when the ECU isn't fully operational. FSCRIPT uses the saved bytes directly. All right, now let's talk about a command that's made specifically for ECU recovery after reflash, and that's did2mm. This command lets you recall a did value from your DAT file and then write that data directly to a specific memory address in the ECU. It's especially useful when you flash a module and suddenly realize some part numbers or serial numbers are gone. What it does, did2mem takes a did that was previously saved with did save and writes it into memory using service 3D, direct memory write. It's meant for those cases where a reflash erased important values like part numbers F188, serial numbers F18C, or custom config DIDs like DE00 or DE01. Syntax. Did the saved identifier like hex F18C, memory address where you want to write it. Byte count, how much to write. Fill with zeros if less than that. Example. This means get the saved value of did F18C from the .dat file. Write it into memory address 0 XA00E0000. Fill 24 bytes total. If the did is shorter, it fills the rest with the zeros. Real-world tip. You'll usually get the memory address from the ECU documentation or from your team. This part's specific to the module. But once you know the address where the part number is stored, Did to mem lets you restore it with one line, no rework needed. All right, now let's talk about the commands used to reprogram ECUs using VBF files in FSCRIPT. The three commands you'll use are prog, prognr, proggnc. They all basically download a VBF file to the ECU, but with small differences in how they handle reset and post-flash checks. Let's walk through each one. First is the prog command. Prog is the standard programming command. It performs the full process. Downloads the VBF file, waits for security if needed. It performs a checksum validation and a reset after flashing. Use this command for the last file in the sequence. This is where you want FSCRIPT to perform checksum validation and do a final ECU reset after flashing. Examples. Check out both the examples. The security seed is optional. If the file needs it, provide it. Otherwise, you can leave it out. Note, all three commands displays progress on lines 3 to 7 of the LCD screen. Next is the prognr command. Prognr is like prog, but skips the reset. Use this for the first file in the sequence, always. Usually, the SBL, secondary bootloader, is the first file you flash. You just want to go straight into programming session without doing a reset. FSCRIPT will enter into 10:02 programming session. Do a security unlock, then start the VBF download. Example, prognr followed by VBF file name followed by security bytes. This will download the SBL without resetting first, which is exactly what you want. Next is the prognc command. Prognc skips the post-flash validation step. Use this for any files in the middle of the sequence. This is for those intermediate files, like data or calibration files, that come after SBL but before the final VBF file. So why to skip validation? Because you can only run the checksum check after downloading all parts, not in between. Check out the example. So again, prognc equals to download file. Don't validate yet? Continue with the sequence. What happens behind the scenes? Behind the scenes, these three commands handle the entire UDS flashing sequence for you. FSCRIPT sends a diagnostics session request to enter programming session, performs a security unlock using service ID 27, then uses service ID 34 to request the download, followed by sending the actual VBF data using service ID 36. Once the full file is downloaded, it sends a hex 37 request transfer exit to tell the ECU the transfer is done. FSCRIPT handles all the protocol complexity behind the scenes, reliably and in the correct order. Real-world tip. Always remember, start a periodic tester present message before you begin flashing. This keeps the ECU session alive during the full reflash process. Do not reset at the beginning. Use prognr for SBL. Don't do checksum validation in the middle. That's what prognc is for. Only validate and reset once, at the end, with prog. Once you get this pattern down, flashing ECUs becomes super predictable and scalable. You can flash as many files you want, no manual intervention needed, and FSCRIPT handles it all cleanly. All right, now let's talk about the security command in FSCRIPT. This is what you use when you want to manually perform a seed key unlock with the ECU outside of an automatic programming commands flow. It's especially useful before requesting or modifying certain DIDs that require elevated access. When you're not flashing but still need level 1 or 3 access, or when you want to do a specific routine. In the first example, we are entering security level 3 using a 5-byte security value. In the next one, we are entering security level hex 61 using a 12-byte security value. Real-world tip. Some ECUs will lock you out if you fail the key 3 times, so be careful when testing. Also, some security levels require a different session to be active, like extended or programming, so always switch sessions first before attempting a security unlock. Let's now take a look at the DTCVL command in FSCRIPT. This command is used to check for the presence of specific diagnostic trouble codes, DTCs, stored in the ECU, and it gives you control over what to do based on that. It's useful when you're building safety checks, running conditional logic before a flash, or validating the results of a test routine. Check out the syntax. The first 2 bytes are high byte and low byte of DTC code. The last 2 bytes will be the status mask and the value you expect after applying the mask. Check out the example. The first 2 bytes is the DTC 0715. Third byte is the mask, and next is the expected value. So basically, if DTC present in the ECU with the status of exactly hex AF. If yes, it shows DTC 0715 found. If not, it prints DTC not found. FSCRIPT internally sends a UDS request 1902, report DTC by status mask, then applies the given mask to the return DTC status byte, compares the result to the expected status. This is great for doing checks before or after flashing, or even after running specific routines. Now, let's talk about how you can move around inside your FSCRIPT program, jump to different sections, or call reusable blocks of code. The 3 commands you'll use for this are go to command, unconditional jump to a label. Go sub command, jump to a label and come back later. Return come back from a subroutine. Before you can jump anywhere, you need a label. That's just a marker in the script. Check out the syntax, just a label name followed by colon. This is where your goto or go sub will land. Labels always end with a colon. Next is the goto command. The goto command jumps directly to a label and continues execution from there. Check out the example. If the VBAT is less than 11 volts, it will go to low voltage label, wherever it is defined, and perform tasks, whatever defined in that label. In this case, it will display battery too low on the LCD screen. Next are the go sub and return commands. Now, if you want to call a block of code and come back after it runs, that's where go sub comes in. Think of go sub as a function call. You go to the block, run it, and then come back to the next line after the call. Every go sub should eventually hit a return. Otherwise, the script will keep running past the subroutine. Return just tells FSCRIPT to go back to where the go sub was called and resume from the next line. Check out the example. Script will jump to check voltage label, check the battery voltage, and then return back. Then it will print come back here on the LCD screen. These control flow commands let you structure your scripts much better, especially when they get longer or more complex. Now, let's talk about how you can move around inside your FSCRIPT program, jump to different sections, or call reusable blocks of code. The 3 commands you'll use for this are go to command, unconditional jump to a label. Go sub command, jump to a label and come back later. Return come back from a subroutine. Before you can jump anywhere, you need a label. That's just a marker in the script. Check out the syntax, just a label name followed by colon. This is where your goto or go sub will land. Labels always end with a colon. Next is the goto command. The goto command jumps directly to a label and continues execution from there. Check out the example. If the VBAT is less than 11 volts, it will go to low voltage label, wherever it is defined, and perform tasks, whatever defined in that label. In this case, it will display battery too low on the LCD screen. Next are the go sub and return commands. Now, if you want to call a block of code and come back after it runs, that's where go sub comes in. Think of go sub as a function call. You go to the block, run it, and then come back to the next line after the call. Every go sub should eventually hit a return. Otherwise, the script will keep running past the subroutine. Return just tells FSCRIPT to go back to where the go sub was called and resume from the next line. Check out the example. Script will jump to check voltage label, check the battery voltage, and then return back. Then it will print come back here on the LCD screen. These control flow commands let you structure your scripts much better, especially when they get longer or more complex. First up, let's talk about the VIN_verify command. This command is all about making sure the tool is connected to the correct vehicle before running any sensitive operation, like a reflash, configuration change, or fleet update. FSCRIPT reads the VIN using OBDII mode 9 and then checks whether that VIN exists in a pre-approved VIN list file saved on the SD card. Check the syntax. VIN file can be a plain CSV file or encrypted file. Check out the example. This will block the script if the current vehicle's VIN is not listed in that CSV. FSCRIPT checks. If the VIN is in the list, script continues. If it's not, it shows an error and exits to the main menu. When would you use this? This is perfect when you're doing a fleet-wide update, you're flashing prototype or secure builds, you want to avoid mistakes like updating the wrong vehicle. I've used this in cases where only 50 vehicles were supposed to get an update. So we loaded a VIN whitelist and used VIN_verify at the top of the script. Super simple. Now let's move on to the FW_version command. This one's all about checking that the MyCANIC tool's firmware is compatible with the script. You don't want someone to run a new script on an old firmware that doesn't support certain commands, right? That's where this check comes in. Check out the examples. The first one checks, is major version =50? The second one checks, is major =50 and minor upwards 11? If not, script exits immediately. Why this is important? Let's say you're using new FSCRIPT features like DID2mem, DAT_check, or advanced logging. Those may not be available in older firmware builds. So FW_version prevents accidental use of newer scripts on outdated tools. Put this right at the top of my scripts so it fails fast if the setup isn't right. Let's take a look at the version command in FSCRIPT. At first glance, it's just a way to tag your script with a version string. But if you include dbg in the version string, you unlock a super powerful debug mode, one that gives you a full-blown raw CAN log of what your script is doing on the bus. What this does: assigns a version tag to your script for tracking, enables generation of a debug log file named FSCR_dbg.log. The number after dbg, like dbg12, controls the maximum number of data bytes logged per CAN message. Check out the example. Since the number after dbg is 20, the debug log will log up to 20 message data bytes. Once logging is enabled, FSCRIPT captures every CAN transaction, whether it's from your script or ECU response, and logs it in a channel-accurate, time-stamped format. Here's a snapshot from the debug log. This shows channel number, timestamp, message length, CAN ID, raw hex data. It's super useful for debugging reflash failures, verifying DID responses, tracing security unlocks, timing out issues with sessions or keep alive. I use this logging mode whenever I'm testing a new reprogramming sequence, dealing with security unlock or handshake issues, need to prove what messages went out and what came back. It's also super helpful when someone says it didn't work. Just open the log file and walk through the steps.